Good afternoon, ladies and gentlemen. It's nice to see you here in these challenging times. My name is Daria and I am third-year student of Moscow State University of Civil Engineering, majoring in Information Systems and Technologies. Our purpose this day is to hear my presentation and to discuss it with all of you later. In this presentation, I would like to focus on something developers need to know about SQL performance, something about indexing in database. First, I will begin with an introduction of SQL performance. SQL performance problems are as old as SQL itself. Some might even say that SQL is inherently slow, although this might have been true in the early days of SQL. But it is definitely not true anymore. Nevertheless, SQL performance problems are still commonplace. The SQL query reads like an English sentence that explains the requested data. Writing SQL statements generally doesn't require any knowledge about inner workings of the database or the storage system. There is no need to tell the database which file to open or how to find the requested rows. Many developers know very little about the processing that happens in database. Consequently, the author is not responsible for slow execution. However, experience proves the opposite. The author must know a little bit about the database to prevent performance problems. It turns out that the only thing developers need to learn is how to index. Database indexing is, in fact, a development task. That is because the most important information for proper indexing is not the storage system configuration or the hardware setup. The most important information for indexing is how the application queries the data. This presentation covers something developers need to know about indexes. To be more precise, the presentation covers the most important type only, the B-tree index. An index makes the query fast. This is the most basic explanation of an index. An index is a distinct structure in the database that is built using the createIndex statement. It requires its own disk space and holds a copy of the indexed table data. That means that an index is pure redundancy. Creating an index doesn't change the table data. It just creates a new data structure that refers to the table. A database index is very much like the index at the end of the book. It occupies its own space, it is highly redundant, and it refers to the actual information stored in a different place. Searching in a database index is like searching in a printed telephone directory. All entries are arranged in a well-defined order. Finding data in an ordered data set is fast and easy because the sort order determines each entry's position. A database index is, however, more complex than a printed directory because it undergoes constant change. Updating a printed directory for every change is impossible for the simple reason that there is no space between existing entries to add new ones. A printed directory bypasses the problem by only handling the accumulated updates with the next printing. An SQL database cannot wait that long. It must process insert, delete, and update statements immediately, keeping the index order without moving large amounts of data. The database combines two data structures to meet the challenge: a doubly linked list and a search tree. These two structures explain most of the database's performance characteristics. The primary purpose of an index is to provide an ordered representation of the indexed data. It is, however, not possible to store data sequentially because an insert statement would need to move the following entries to make room for the new one. Moving large amounts of data is very time-consuming, so the insert statement would be very slow. The solution to the problem is to establish a logical order that is independent of physical order in memory. The logical order is established via a doubly linked list. The data structure is called a doubly linked list because each node refers to the preceding and the following node. It enables the database to read the index forwards or backwards as needed. It is thus possible to insert new entries without moving large amounts of data. It just needs to change some pointers. The physical location of the new node doesn't matter because the doubly linked list maintains the logical order. The database uses doubly linked list to connect the so-called index leaf nodes. Each leaf node is stored in a database block or page. That is the database's smallest storage unit. All index blocks are of the same size, typically a few kilobytes. The database uses the space in each block to the extent possible and stores as many index entries as possible in each block. That means that the index order is maintained on two different levels: the index entries within each leaf node and the leaf nodes among each other using a doubly linked list. This figure illustrates the index leaf nodes and their connection to the table data. Each index entry consists of the indexed columns and refers to the corresponding table row. Unlike the index, the table data is stored in a heap structure and is not sorted at all. There is neither a relationship between the rows stored in the same table block, nor is there any connection between the blocks. The index leaf nodes are stored in an arbitrary order. The position on the disk doesn't correspond to the logical position according to the index order. It is like a telephone directory with shuffled pages. If you search for Smith but first open the directory at Robinson, it is by no means granted that Smith follows Robinson. A database needs a second structure to find the entry among the shuffled pages quickly, a balanced search tree, in short B-tree. This figure shows an example index with 30 entries. The doubly linked list establishes the logical order between the leaf nodes. The root and branch nodes support quick searching among the leaf nodes. The structure is a balanced search tree because the tree depth is equal at every position. That means that the distance between root node and leaf nodes is the same everywhere. The following figure shows an index fragment to illustrate a search for the key 57. The tree traversal starts at the root node on the left-hand side. Each entry is processed in ascending order until a value is greater than or equal to the search term, 57. In the figure, it is entry 83. The database follows the reference to the corresponding branch and repeats the procedure until the tree traversal reaches a leaf node. The tree traversal is a very efficient operation. It is the first power of indexing. It works almost instantly, even on a huge data set. That is primarily because of the tree balance, which allows us accessing all elements with the same number of steps, and secondly because of the logarithmic growth of the tree depth. Despite the efficiency of the tree traversal, there are still cases where an index lookup doesn't work as fast as expected. This contradiction has fueled the myth of the degenerated index for a long time. The first ingredient for a slow index lookup is the leaf node chain. Consider the search for 57 in that figure again. There are obviously two matching entries in the index. At least two entries are the same. To be more precise, there can be further entries for 57. The database must read the next leaf node to see if there are any more matching entries. That means that an index lookup not only needs to perform the tree traversal, but it also needs to follow the leaf node chain. The second ingredient for slow index lookup is accessing the table. Even a single leaf node might contain many hits, often hundreds. The corresponding table data is usually scattered across many table blocks, as at the first figure. That means that there is an additional table access for each hit. As a result, an index lookup requires three steps: the tree traversal, following the leaf node chain, fetching the table data. The tree traversal is the only step that has an upper bound for the number of accessed blocks, the index depth. The other two steps might need to access many blocks. They cause a slow index lookup. Okay, let's sum it up. An index is a distinct structure in the database that is built using the createIndex statement. An index makes the query fast. The database combines two data structures to meet the challenge: a doubly linked list and a search tree. The tree traversal is the most efficient operation, but the tree traversal is only a step that has an index depth. So the other two steps, following the leaf node chain and fetching the table data, might need to access many blocks. They cause a slow index lookup. Thank you for your attention. See you.